In this video, we're going to work through several applications of first-order linear differential equations. We'll start by setting up and solving differential equations that model real situations, including Newton's law of cooling, mixing problems, population growth with harvesting, and an RL series circuit. For each application, we'll focus on how to translate the given information into a differential equation, solve it step by step, and then interpret the solution. Let's get started. In a Newton's law of cooling problem, the rate of change of the temperature of an object is proportional to the difference between the object's temperature and the surrounding temperature. Suppose a cup of coffee is initially at 180 degrees Fahrenheit and it's placed in a room where the ambient temperature is 70 degrees Fahrenheit. After 10 minutes, the coffee has cooled to 140 degrees Fahrenheit. We're going to do three things. The first thing that we're going to do is set up and solve the differential equation for the temperature capital T of T. We're then going to find the temperature after 25 minutes. And then the last thing that we're going to do is we're going to find how long it takes for the coffee to reach 90 degrees Fahrenheit. Let's first set up and solve the differential equation. Newton's law of cooling tells us that the change of temperature with respect to time, dt dt, is proportional to the difference between the object's temperature, which is capital T, and the surrounding temperature, which in our case is 70 degrees. So we're going to subtract 70 degrees. This cup of coffee is going to decrease in temperature because it starts at 180 degrees, but the room temperature is 70 degrees. So we're going to make an assumption, and we're going to assume that the change in temperature with respect to time can be written like this: minus K times T minus 70 degrees. That minus K just indicates that the rate of change of the temperature is going to be decreasing. Let's go ahead and highlight this because this is our differential equation, and we need to add one more thing to it. We need to add an initial condition. We are told that the cup of coffee is initially at 180 degrees. So we're going to notate this by T of 0 is equal to 180 degrees. Now what we're going to do is solve this differential equation. Notice that our equation is what we call a separable differential equation. I have a video on separable differential equations if you want to review that. We're going to start by separating the variables. Let's put the temperature, capital T, on the left, and let's put the time, little t, on the right. We're going to write this as dt all over T minus 70 degrees is equal to minus K d little t. Now we can integrate both sides. On the left, we're going to get the natural log of the absolute value of T minus 70 degrees. And on the right, we get minus K little t plus our arbitrary constant that I'm going to call C1. We want to solve for capital T, so we need to exponentiate both sides of the equation, and that'll get the t out of the natural log. We have e to the natural log absolute T minus 70 degrees is equal to e to the minus kt plus C1. On the left, we just have T minus 70 degrees. And then our right-hand side, I'm going to split up as e to the C1, that's our constant term, times e to the minus kt. Now let's get rid of the absolute value on the left. So we just have T minus 70 degrees, and we'll bring the plus minus over here to the right. That's from the absolute value. And now let's get capital T all by itself. I am going to rename this constant right here, and I'm going to call that C. So we have C e to the minus kt plus 70 degrees. Notice that our solution has two constants in it, C and K, and we have to get rid of those. Whenever you have two constants that you want to get rid of, you need two conditions. And we actually have that. We had that T of 0 is 180 degrees. And then we were also told that after 10 minutes, so that's capital T of 10, the coffee has cooled to 140 degrees. So now we have our two conditions and we can solve for our two constants. Let's do the initial condition first, T of 0. So we have T of 0 is going to be C, because e to the 0 is 1, plus 70 degrees, and that's 180 degrees. So that tells us that C is 110 degrees. Let's go ahead and put that back into our solution. We have 110 degrees times e to the minus kt plus 70 degrees. Now we can solve for k. That's always the harder one. Let's go over here to the right and let's use our second condition. We're going to let t be equal to 10. So t of 10 is equal to 110 degrees times e to the minus k times 10 plus 70 degrees, and this is equal to 140 degrees. Let's now pull the 70 degrees over to the right and divide by 110. So this gives us e to the minus 10k is equal to 70 degrees divided by 110 degrees. So that's just 7 over 11. Now we want to solve for k, or we can also solve for minus k. That might be easier. To do that, let's take the natural log of both sides, and that is going to get our k, or the minus k, out of the exponent. We then have minus 10k is the natural log of 7 divided by 11. And let's go ahead and let's solve for minus k. So let's say minus k is going to be natural log 7 over 11, all divided by 10. We are running out of room, so I am going to go ahead and write this equation for temperature and our expression for minus k over on the next page. Now we can go ahead and substitute in minus k. This gives us our temperature is equal to 110 degrees times e to the natural log 7 over 11 times t over 10 plus 70 degrees. I want to show you how to do this next part because I think it's confusing. If you have e to the a times b, you can write this as e to the a raised to the b. So we're going to say that this part is our a and that part's our b. This gives us our temperature is equal to 110 degrees times e to the natural log 7 over 11 raised to the t over 10 plus 70 degrees. Now we can write the final answer. Our temperature is 110 degrees. The e and the natural log cancel out, and we have a 7 over 11 to the t over 10 plus 70 degrees. And there's the solution to our differential equation. The key takeaway here is that our temperature decays exponentially. And the reason for that is this number here, 7 over 11, is less than 1. Now let's go on to our second part. In part 2, we want to find out what the temperature is after 25 minutes. So all we have to do for this one is just plug in that our time t is 25. This gives us 110 times 7 over 11 to the 25 over 10 plus 70 degrees. You can go ahead and put that in your calculator, and if you do, we end up with a value of 105.5 degrees. And that tells us that after 25 minutes, our coffee is at a temperature of 105.5 degrees Fahrenheit. Let's now look at our third question. That one's a little bit harder. This question is asking, at what time is the temperature of the coffee equal to 90 degrees? So what we're going to have to do is take our expression for our temperature. It's highlighted up there in green. It's 110 degrees times 7 over 11 to the T over 10 plus 70 degrees. And we're going to set this equal to 90 degrees. What we have to solve for then is little t. Let's go ahead and pull the 70 to the right and divide by 110. This gives us 7 over 11 to the T over 10 is 90 minus 70, which is 20. And we're going to divide that by 110. So this gives us 2 over 11. Now to solve for t, we need to get it out of the exponent. So I'm going to take the natural log of both sides. This gives us natural log 7 over 11 to the T over 10 is equal to the natural log of 2 over 11. We can pull the T over 10 out in front, and we have natural log of 7 over 11 is equal to natural log 2 over 11. We can then divide by natural log 7 over 11, and we can go ahead and multiply by 10 at the same time. So T is equal to 10 times natural log 2 over 11, all divided by natural log of 7 over 11. When you put this in your calculator, you find that this is equal to 37.7, and our units are minutes. This tells us that our coffee reaches 90 degrees in 37.7 minutes. And that's all there is in solving a Newton's law of cooling problem. In a mixing problem, what you're going to do is track the amount of a substance in a tank over time. Suppose a tank initially contains 100 gallons of pure water. Brine containing 2 pounds per gallon of salt flows in at 3 gallons per minute, and then the mixture flows out at also 3 gallons per minute. What we want to do is set up and solve the differential equation for the amount of salt that we're going to call y of t. We can then use our solution to find the amount of salt after 20 minutes. The differential equation for the amount of salt is going to be the rate of change of the salt is equal to some quantity. So let's write down dy dt, that's the rate of change of the salt. It is going to be equal to the rate in minus the rate out. That just means it's going to depend on the salt per minute in minus the salt per minute out. And that's what we have to figure out. Let's look at the rate in first. We are told that brine is flowing in, and that has a concentration of 2 pounds per gallon. And it's flowing in at a rate of 3 gallons per minute. So we're going to multiply this by 3 gallons per minute. And this is equal then to 6 pounds per minute. Now let's look at the rate out. We are not told how many pounds are flowing out because that's what we want to find. So the amount going out, we're going to say is the amount of salt per gallon. And we're told that it flows out at 3 gallons per minute. I'm going to highlight this because I think that's the hardest part. Now we can decide what the salt per gallon is equal to. The salt is our variable y, and our tank holds 100 gallons of water. So we're going to divide y by 100. This gives us 3y divided by 100 pounds per minute, because y is in terms of pounds. Let's now put this into our equation. We have dy dt is equal to our rate in, which we found was equal to 6, minus our rate out, which was 3y divided by 100. Let's highlight this because that is our differential equation, and we need to add a condition to that. We are told, let's look back up here, that initially the tank contains pure water. That means the amount of salt initially is 0. So we can say down here that y, which is the salt, at time 0 is equal to 0. And there's our initial condition. Now we are all set to go ahead and solve this differential equation. Let's rewrite the right-hand side, and I think when we do that, we'll be able to tell what type of equation we're working with. Let's rewrite the right-hand side as 600 minus 3y divided by 100. Now you can see that we are working with a separable differential equation. So let's go ahead and let's move all the y's to the left and the t to the right. This gives us dy all divided by 600 minus 3y is equal to dt divided by 100. Now we can go ahead and integrate both sides. On the left, we have a minus 1/3. That is because the derivative of y is minus 3. And we have a natural log, absolute value 600 minus 3y. And then on the right, we just have 1 divided by 100 times t plus an arbitrary constant that I'll call c1. Let's multiply both sides by minus 3. So on the left, we have natural log 600 minus 3y. And then on the right, we have minus 3 over 100 times t minus 3c1. We can now exponentiate both sides of our equation. On the left, the e and the natural log are going to cancel out. So on the left, we're just left with 600 minus 3y. And on the right, we have e to the minus 3 over 100 times t. And then let's write this and split up the exponential like this. Now let's get rid of the absolute value. So we're going to get a plus or minus, and we're going to put that on the right-hand side. So we have plus or minus, and I'm going to change around our exponents. I'm going to write this one first, and then I'm going to write the next one. The reason I'm doing that is we can now call this constant C2, and then we can solve for y. Let's first write 600 minus 3y is equal to C2 e to the minus 3 over 100 times t. Let's pull the 600 over to the right. So we have minus 3y is equal to C2 e to the minus 3 over 100 times t minus 600. And then we'll divide by minus 3. And we get y is equal to C2 divided by minus 3 times e to the minus 3 over 100 times t plus 200. Let's rename our constant once more. We'll call that c. And over here on the left, we can write down our solution. Y is equal to 200 plus c times e to the minus 3 over 100 times t. Now we need to solve for c, and we can do that by using our initial condition that y of 0 was equal to 0. So let's plug in that t is equal to 0. This gives us y is equal to 200 plus c times e to the 0, which is just 1, and this is equal to 0. So this tells us that c is equal to minus 200. And we can write our solution as y is equal to, let's see, they both have a 200. So I'll pull that out, and we have 1 minus e to the minus 3t over 100. And there's the solution to our differential equation. Now we also need to put units with this. Y is the amount of salt, and the amount of salt is measured in pounds. So let's put pounds over here. The second part of our problem is to find the amount of salt in the tank after 20 minutes. So that means we need to find Y at 20. Let's write down what we had for our Y of t. It was 200 times 1 minus e to the minus 3t over 100. Now all we have to do is let t be equal to 20. This gives us 200 times 1 minus e to the minus 60 over 100. And this is just 200 times 1 minus e to the minus 0.6. You can put that in your calculator, and we find that our answer is approximately 90.24 pounds. So we now know that the amount of salt in the tank after 20 minutes is 90.24 pounds. And that's all there is to solving mixing problems. A population growth with harvesting problem models how a species population changes over time when it's subjected to harvesting, such as fishing. Suppose a fish population grows at a rate proportional to its size with proportionality constant 0.04 per year. Initially, there's a population of 10,000 fish, and fish are harvested at a constant rate of 200 fish per year. What we're going to do is we're going to set up and solve the differential equation for the fish population capital P of t. Once we have the solution, we can use that to describe the long-term behavior of the fish population. Let's first set up our differential equation. Our differential equation starts with the change in population with respect to time, and we're going to write that as d capital P dt. And the change in population is going to be equal to the growth rate minus the harvesting rate. We are told that the population grows at a rate proportional to its size. So the way we write that mathematically is we have a proportionality constant k, and then we have a p. That just means that the rate dp dt is proportional to p. And then we subtract off the harvesting rate, which we're told is 200 fish per year. So we just subtract off 200. Now we can go ahead and substitute in what k is. We are told that we have a proportionality constant 0.04 per year. So we can write this as d capital P dt is 0.04p minus 200. And we can also add on our initial condition. We are told that the initial fish population is 10,000. So we can say that P at 0 is equal to 10,000. And there's our differential equation and the initial condition. Now what we need to do is solve this differential equation. This differential equation can actually be solved two ways. This is a linear ordinary differential equation, and it's also a separable ordinary differential equation. I am going to solve it as a separable differential equation. Before we go ahead and separate the variables, I want to multiply by 100 just to get rid of that decimal. So let's say that this is 100 dp dt is equal to 4p minus 20,000. Now let's separate the variables. On the left, we have 100 dp, and we're going to divide this by 4p minus 20,000. And on the right, we get dt. Now we can go ahead and integrate both sides. We have 100, and because of the 4 here, our derivative needs to be 4 dp. So we are going to have to divide by 4. And that gives us natural log absolute value 4p minus 20,000. And on the right-hand side, we have a t, and then we add on our arbitrary constant plus c. Let's go ahead and solve for c. Let's use our initial condition that p at time 0 is 10,000. So this on the left, we have 25 natural log absolute value. 4 times 10,000 gives us 40,000 minus 20,000 is equal to t, which is 0, plus c. So this tells us that c is equal to 25 natural log of 20,000. We'll drop the absolute value because it's positive. Now we can rewrite our solution as 25 natural log absolute value 4p minus 20,000 is equal to t plus c, which is now 25 natural log 20,000. Let's now combine our natural logs. So I'm going to pull the one on the right over to the left. And we just have a t on the right. On the left, we have 25 natural log 4p minus 20,000, all divided by 20,000, is equal to t. Let's go ahead and divide by 25. And then we can exponentiate each side, and that gives us 4p minus 20,000, all divided by 20,000, is equal to e to the t over 25. Let's now solve for p. So we have 4p is equal to 20,000 e to the t over 25 plus 20,000. And then all we have to do is divide by 4, and we get p is equal to 5,000. Hang with me, we are almost done. And we can combine this, pull out the 5,000, and then we have 1 plus e to the t over 25. And let's put in units, we are working with fish. And there's the solution to our differential equation. Notice that because this term right here is positive, our fish population is going to grow exponentially. And that's exactly what we have to answer for our second question. We want to describe the long-term behavior of the fish population. We can write that as the limit as t goes to infinity of p of t is equal to 5,000 times 1 plus e to the infinity, and that is equal to infinity. So we can say that our population grows exponentially. Before we're done with this problem, I want to show you one more interesting thing that relates to the population growth. Let's go back up here and look at this part of our equation. We are going to have what's called an equilibrium solution, meaning the population is not going to grow or decline, and that's going to happen when this right-hand side is equal to 0. If we solve this for p, we get that p is equal to 5,000. This tells us that if our initial population is greater than 5,000, we're going to have exponential growth. And if it's less than 5,000, we're going to have exponential decay. And our population will become extinct. We're going to look at an RL series circuit problem. In this type of problem, Kirchhoff's voltage law leads to a differential equation for the current that we're going to call I of t, and we're going to solve that equation. We're told that a 12-volt battery is connected to a series circuit in which the inductance is 2 henries and the resistance is 8 ohms. We want to determine the current I of t if the initial current is equal to 0. After we find the current, we're then going to determine what the steady state current is. Let's start by writing down what our variables in our circuit diagram are equal to. E is the electromagnetic force, and it is equal to 12 volts. The inductance, L, is equal to 2 henries. And then the resistance, R, is equal to 8 ohms. The differential equation for an RL series circuit looks like this. It's L times the change in current with respect to time plus the resistance times the current is equal to the electromagnetic force as a function of time. In our case, it's going to be a constant. Let's now put in what L, R, and E are equal to. L is equal to 2, so we have 2 di dt. And then the R is 8, so we have an 8I, and that's equal to 12. Let's go ahead and divide by 2, so we have di dt plus 4I is equal to 6. And we have an initial condition for this. We are told up here in yellow that the initial current is 0. So we can say that I at 0 is equal to 0. And there's the differential equation that we need to solve. This differential equation is called a linear differential equation. And we can solve it by using an integrating factor. That's what we're going to compute first. Our integrating factor depends on this constant 4 that multiplies I. Our integrating factor, mu of x, is e to the integral of 4 times dt. So this is just e to the 4t. We're going to take that integrating factor and we are going to multiply every term in our equation by that. So we have e to the 4t times di dt plus 4e to the 4t times I is equal to 6e to the 4t. Our left-hand side we can write as d dt of our integrating factor e to the 4t times I. It always works out that way. And then on the right we have 6e to the 4t. Now we can go ahead and integrate both sides. On the left, we just have e to the 4t times I. And then on the right, we have 6e to the 4t, but we need to divide by 4. And then we'll add on our arbitrary constant c. If we solve for I, we find that I is equal to 3/2 plus ce to the minus 4t. Now let's go ahead and solve for c using our initial condition that I at 0 was equal to 0. So we have I at 0 is 3/2 plus c times e to the 0, which is just 1, and that's equal to 0. So this tells us that C is minus 3/2. And let's write this as minus 1.5. And we can write this one as 1.5 as well. So over here on the left, we can write down that I of t, that's our current at time t, is equal to 1.5 times 1 minus e to the minus 4t. And there's our expression for our current at time t. And of course, we need units. Current is measured in amps. So let's write down amps. And then we'll highlight that as well. Now we can answer the second question, and that is to determine the steady state current. To do that, all we have to do is take the limit as t goes to infinity of our current. So we have the limit as t goes to infinity, 1.5 times 1 minus e to the minus 4t. This term here is e to the minus infinity, which is 1 over e to the infinity, which is 1 over infinity, which is 0. So this tells us that our answer is equal to 1.5 amps. And that's our steady state current. And that's it. You now know how to set up and solve first-order linear differential equations for a variety of applications, including cooling, mixing, population models, and electric circuits. You should now be all set to work through some application problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.